Alright, so we're going to continue our analysis of the revt service DLL file. Now, the main goals are to identify the offsets from the image base of the virtual functions for the evtx file class. We also got the task to fill out as much of the structure definition as you can, and find the probable actual size of the class object. Now, before I walk through the solution, again, I'll just reiterate, if you got stuck at any part during your own attempts, feel free to use this solution video as just enough of a help to get you past the point that you are stuck at, and then pause the video, continue on your own, and come back and resume this. That'll help engrave it kind of in your own mind as you go through and explore the binary yourself. Really, that's how you're going to ingrain a lot of this information. So with that said, let's jump into it. I'm probably not going to dive too deep into everything, but we will identify the offsets, we will find the probable actual size, and we'll find out quite a bit of what the structure is. I'm not sure how far I'm going to go into it, because at some point it's not really at some point once you've done enough of them, it's not really a difficult thing. It's more just a time-consuming process. So let's jump into it. I've got it loaded up here in Ghidra. I'm going to double-click it. We're going to analyze it for the first time. PDB Universal, I'm going to have enabled, and I'm going to allow it to search remote servers, so it can pull the symbols down from the Microsoft symbol server. I'm also going to enable periodic function signature override and x86 propagate external parameters. Okay, I'm going to hit analyze. I'll wait for it to finish. It shouldn't take too long. So this is a fresh analysis, so I'm starting from scratch here in my analysis again. Just give it another moment to finish analyzing. I'll modify the views because I don't want the listing view to be so large. For the majority of the reversing that I do, like the decompiler is generally enough to look at. Sometimes I'll have to look at the actual assembly or disassembly to fix up decompilation errors with like parameters and things like that. There are some cases though where I work primarily with assembly, and that's in cases where you're analyzing an obfuscated binary, or a binary that does a lot of anti-static analysis kind of techniques in there, like mixing code and data in the text section, for example, that can really mess with some decompilers, but we'll tackle those a bit later on. Okay, so analysis is done, and we know that, from the little kind of write-up here, we're looking at the evtx file. So with Ghidra, it has this classes folder, and it'll have the evtx class here. I'm just going to type evtx file here. And with the evtx file class, what I'm looking for in this class is, first of all, the virtual function table. That's going to help me identify the offsets. So if I clear the filter and just look for the VF table, which is right here, it'll take me in the listing view to the VF table where it shows the virtual functions. And here there's 4 virtual functions that live at these function addresses. Now, why the offsets are interesting, they come into play for various reasons. One is, no matter where the function's loaded in memory, the offset's going to be the same. And what I mean when I say that is, these addresses here, right, 1800F4C38, that's like a hard-coded address, right? But if I ran this program on Windows, this address likely isn't even going to be valid. And the reason for that is binaries, as we saw when we were analyzing the PE32 header, they have a preferred base address in the header. And that's the base address that they would like to be loaded at. But with ASLR and things like that, a lot of binaries are now marked as relocatable, so that, or even have ASLR enabled, such that their base address can be randomized. So what that means is, let's take this query function, for example. If I double click it, in this disassembly in Ghidra, this query function lives at this address 1800.262.A0. Now, if I had this process running and I wanted to put a breakpoint on this query function, I can't put a breakpoint on this hard-coded 1800.262.A0 address in my debugging session. Or most likely I wouldn't be able to if I was debugging an already running process, because the query function is likely not actually living at this address thanks to ASLR and relocation. So what you want instead is an offset from the base address, because the offset is always going to be the same. And what I mean by that is, say the binary, right, is loaded at a base address of 14000, and say the query function lives at, let's zoom this in a bit, lives at 14100. Now the offset is the address of the query function minus the base address, which means the offset in this case is 0x100, right? Because 14100 take away 14000 is 0x100. Alternatively, when it's like this, you can just straight up grab the last three digits. As long as the first two here are 14, then the only difference is the last three. And since the last three here was 0, the last three here is 100, which matches the offset 100. So you can eye it that way as well, depending on what the base address is. So if query is at offset 100, that's going to be the same no matter what the binary is. If the binary was loaded at 0x17100, then if we apply the offset of 100, then query in this case lives at 17200, right? Because 17100 plus the offset equals to 17200. So you can see in both examples, no matter what the base address is, whether it's 14,000 or 17,100, the offset is still exactly the same. So we can find the query function by just applying that static offset to the base address. And you would get the pointer to the proper query function. So that's why offsets are useful to know when we look into debugging and things like that, especially if we don't have symbols. Note, of course, that these offsets are only going to be valid for like the specific version of the file you're analyzing. Because if you have a different version of the DLL or the target, it could have been recompiled and the compiler could have changed the offsets and things like that. So this is only valid for the specific version of the file that you are analyzing. In this case, if I want to see what the base address here, there's a couple ways to do it. One way is to just view the memory map in Ghidra by going Window Memory Map, and you want to find the lowest address, which is normally named headers. And you can see the start address is 18 followed by, I don't know how many zeros this is, 1, 2, 3, 4, 5, 6, 7, like 7 zeros. And that's the base address. Now, since the first two digits are 18 and the rest are zeros, it's actually very easy to find the offset, because if we look at our query function, the first two digits are still 18, which means our offset is just this remaining bit, which means the offset to query from the base address of this DLL is 262A0. That's the offset, 262A0. Done. That's the offset for query. Now you go back to the virtual function table and you can find the offsets for the other ones in the same manner. This one, for example, is 7D7F0. The deleting destructor one is at 26620. Simple. And this is the address of the first instruction in that function. That's the address of that function. Cool. So we figured out how to find that. So that part's done. The next main part is really just identifying stuff related to the EVTX structure or the EVTX file. First thing I'm going to do is go to the constructor for it, which has the same name as the class name. Now, parameter 1 is going to be an EVTX file pointer, and we already have that type thanks to symbols. It's not filled with the actual structure, but the naming is there. So I can do Control-L to change the data type to an EVTX file pointer. And I'm just going to rename it to this. All right, now I want to actually create a structure from this object. So I'm going to right click it and do autofill in structure. All right, we have some items now. Now, field 0 offset 0 we know is a pointer to the VF table. So I'm going to do Control-L to retype this field. This is going to be a function pointer. No, not a function pointer. It's going to be a VF table pointer. We know that the VF table in this case is 4 entries, right? 1, 2, 3, 4. So it's actually a pointer to an array containing 4 function pointers. So how am I going to declare that? We need to create a structure. So I'm going to go window. Let's see, what's the best way to do this? Data type manager, perhaps. That's here. Can I add a data type? New. Okay, I can right click the revtservice.dll data type, and I'm going to create a new structure. Unless this VS table already has a structure. Does it? No, it's just defined as a undefined pointer. All right, I want to give this VF table an actual structure because I don't think there's a proper VF table structure here. So let's right click revtservice in the data type manager, go new, go structure. Okay, in this case, this structure name is going to be a avtx file underscore VF table. It's going to be the VF table for the avtx file specifically. It's going to have 4 pointers. So this is going to be maybe a farproc pointer, which is a 64-bit pointer to a function. So we're going to have 4 of them. Farproc pointer. Oh, whoops. Farproc pointer. Yep. Farproc pointer. And the 4th one, farproc pointer. Okay, we have 4 pointers. This is the VF table. It has 4 pointers in the structure. And they are 8 bytes each, 30, 38, 40, 48. Okay, so what happened to it? Here it is. All right. The name of this first one is, what was it? Well, it's just VF table 1, but it's a pointer to that. I'm just going to give it, I'm not going to actually name it the function pointer. Oh, I'm going to say p destructor for pointer to destructor. Next one is p query, pointer to the query function, pointer to the clear function, and pointer to the get log file info function. Okay. Now, these data types, you can see the mnemonic here is it returns just an int and it takes a void. I could actually fill it out with the proper parameters that they take in that, but there's really no point to doing that at the moment. I'm just putting in enough information to make it a little bit more clear when I'm analyzing it, not to be like super detailed for no particular reason. You can do that if you want to, but it's kind of a waste of time. So let's save this. And let's see how this goes. Now let's change this field 0x0 because we know that's now a pointer to the VF table structure we created. So this is going to be a VF table pointer. I didn't create a VF table pointer. So let me fix that up. I need to create a new type def, which is oh, how do I create a pointer to that? Do I just create a structure? Let's see. What's a car pointer defined as? I just want to view this. I really just want to view what a car pointer is defined as here. Let's see. Pointer to ucar, type def on ucar. Oh, maybe I can create a pointer that way. Okay, so I find the type I just created, the evtx file VF table. I right click that, I create new, and I click the first one, pointer to it. Yes, I want to create a pointer type to it. Okay, cool. I've created the pointer type. Now that I did that, I should be able to retype this field as a pointer to the VF table. Yes, now I see the pointer. And I apply that. Done. And I'm going to rename this as VF table. So now that this pointer has a VF table entry, that is a VF table for the evtx file pointer, which makes entire sense. That's perfect. Now, this field is parameter 3. What is parameter 3? Well, let's see what calls this constructor. We have a few places calling it. 1, 2, 3. Actually, let me go back. Here it is, 1, 2, puvar11. puvar11 is the dereferenced puvar6. puvar6 is file manager get file. Get file returns. What does this return? Well, this must return something because if we go back, this is set to the return value of that, and then it's dereferenced and set to this, and then this is actually used in the third parameter to the evtx file call here. See, this is the third parameter that we want to find out what it is. And that's set to the dereferenced PU of R6, which comes from get file. So get file, let's change the return type on this to a, just for now, a car pointer. Because I know it's going to be a pointer, we just don't know what to. Now let's see what the decompilation says it returns. It says it returns this. Okay. It doesn't think that actually sets to anything. How many parameters does this actually take? 1, 2, 3, 4, 5, 6. 6 parameters? Okay, it's probably one of the functions it's calling internally here that it doesn't realize also returns something. What's this PPU var 3? Because that gets set to things, but it doesn't look like it actually does anything with it. I imagine this variable is important. It just hasn't realized it. Okay. Now, at this point, I could continue diving in further on that to figure out what it is. But if we have other usages of this constructor in other places of the program, it can be quicker just finding some other place to analyze it that could be quicker. So right now we're looking for what is parameter 3. So let's go to this other incoming reference, get log for container channel. If you don't have this function call trees windows, by the way, you can go to window and do function call trees, and it'll show you this little window showing incoming and outgoing references to whatever you're looking at. Okay, in this case, parameter 3 is PA-var1, which is AVAR3, which comes from this get file object call. Now, this actually says that it returns a file class. So get file object returns a file object pointer into AVAR3, and that gets allocated to PA-var1, and that gets thrown out into evtx file here. That's this third parameter. It's going to be a well, actually, if it's dereferenced, if it's a dereferenced file object, right? Let's say AVAR3. What type does it have it as? A autoref class file. Which really means it's probably just a file pointer, right? Let's see what's happening to that. It's getting dereferenced and put into RSI. Where's this line? Oh, okay. It's just being dereferenced and it's being put into RSI. And then here, RSI gets moved into R8. Okay, so it's just a dereference of the file pointer, assuming that ivar1 is a file pointer. Well, that gets it from this plus 0x18. Where's this plus 0x18 here? That's this, and what does it do with it? Let's expand this. It dereferences it and sets it to dereferenced PLVAR2, which comes from open log with retry, which opens a log file and returns a pointer to a file object. So it's supposed to be a file pointer. Okay. So what does it actually do with it? If it doesn't equal to 0, then it gets an offset to it, increments it, and does a few things. It gets a really big offset to it, actually. So this is most likely going to be a pointer. Well, if I look at the file object, let's look at the VF table for the file class. It's autoref class file, which is just this file struct or file pointer. Here it is. Here's file. Okay. Um, okay. So file should have a constructor. Let's look at the constructor. What happens in the constructor for file? This will tell us more information about what actually happens to it. So it looks like the file object, it doesn't seem to have a VF table. You can see in the constructor, there's no actual VF table. However, it does have a whole bunch of variables and variables associated with it at a whole bunch of different offsets. So let's fill out this file pointer type. Let's change parameter 1 here to a file pointer, and let's autofill in the structure. Okay, now it's auto-filled in with the structure. Cool. Now that we've defined the file pointer and we know that this is passed through as argument 3 to our evtx file constructor, let's go to our evtx file constructor function. Okay. Parameter 3, I believe, was the file pointer. So let's retype this as a file pointer. Okay. Now, parameter 3, we can see accesses to it as, parameter 3 interpreted as a file pointer referencing some address, equals to this plus 1 type thing. What's this data type? So that's offset 338. This is a large structure. Okay. This is just incrementing it. It's treating it as an int. What it's doing is dereferencing itself and then just adding 1 to it. So it's like this field equals to the same field plus 1. So it's just doing an incrementation on it. So that's probably some sort of reference counting. It's doing it as a D-word pointer. So perhaps this field is actually just a 32-bit value because it's treating it as a 32-bit value in assembly. So let's quickly retype this to reflect that. I'm going to make this an int, and I'm going to name it ref count. So now that I did that, this looks a lot more clear, doesn't it? Parameter 3 ref count equals to parameter 3 ref count plus 1. That makes entire sense. Let's see where else ref count is used. It's probably used in the destructor, right? If we go to the destructor, do I see the ref count being used here? Surprisingly, no. But that could be in the file destructor, because you can see here that it's treating 0x10 as a file pointer because it's destructing it. And perhaps the file destructor clears up that ref count. Let's see. Well, this is also ref count because it gets set to the pointer. This is ref count pointer then. P ref count. And it's a int pointer. Yes. This gets set to the ref count. The disassembly here, decompilation here is a bit ugly, but we can see that pointer to ref count gets set to the address of the ref count. Then the ref count dereferences that. So at this point, this ref count here matches the actual ref count, and it just minuses it by 1, right? The pointer to the ref count gets dereferenced and gets set to the pointer of the ref count plus -1, which is the same as just -1. So this really does look like a ref count. In the destructor for the file object, it gets decremented by 1. But in the EVTX file handle constructor, it gets incremented by 1. It's directly. So it's some sort of reference counting. And the fact that we identified this field as a reference counting field is very useful, because there's lots of 0 days and bugs that come from incorrect reference counting, where perhaps you can overflow the reference count so that's such that it reaches 0 and it gets freed somewhere, or you can decrement it or just mess it up such that it's no longer an accurate reference count. That can cause a lot of bugs. So the fact that we've identified a reference count variable here could be very useful for that type of analysis. And you can see here that field 6 0x10 gets set to parameter 3. And we already determined that parameter 3 is a file pointer, right? I'm going to rename it to just p file, right? This is a pointer to a file. And now we know that this field in our EVTX file is a file pointer. So let's retype this to a file pointer. And let's rename it to p file. Done. Now when we go back to the EVTX destructor, you can see that it passes through the address to the p file in this release. So that's cool. Yeah, at this point, we're starting to actually fill out the file pointer, the file structure, as well as the EVTX file structure. You know, with our EVTX object, we've got the VF table here. We've got the pointer to a file. We've got a reference count that we found. And we could just go through this process and fill out everything else. But, you know, I think I've kind of gone through enough of it at this point that I can skip to the next part of determining the size of the EVTX file structure. So right now, the EVTX file structure Ghidra thinks it's 0x4a because we created that structure based off this function. And Ghidra can only determine the size when it sees accesses to it, right? If it sees an access only up to 0x, 4a minus 1 or something, it can't know if there's actually more to this structure or not unless it sees it being accessed in the code, right? It's only figuring out what the structs are and what the size of the struct is based on how it sees it being used in the disassembly. But not all of the structure variables may actually be used or touched in this constructor. So let's see if we can figure out if there's more to it. And the way you can find that is a couple things. You can first, you need to see if you can see any accesses to this structure that goes beyond the what Ghidra's size estimate is. So let's see if we can find that. We can also, I'm going to give this a name. It's undefined. It's probably not used. Actually, 0x40. So the ones with the question marks here, they're there because Ghidra hasn't actually seen it really be used properly yet. The last one it saw got used was this one, which I'm going to name. Well, actually, I'm not going to name it anything. I just want to kind of find where it's used. So I'm going to right-click this last one that was used, and let's see if I can find references to it somewhere. Just really want to find cross-references to this thing. How can I find cross-references to it? Well, actually, if it found it being used, it must be used in this function somewhere. Here it is, field 0x48. Now, right now, this 0x48 field, it doesn't know what type it is. What type did it give it? It gave it just a 1-byte type. It doesn't even know what 0x48 is. So let's give that a proper type. bvar1 comes from, and the reason why giving it a proper type may help us with the size, because if it thinks that the field is like 1 byte, but in actuality it's 2 bytes or 4 bytes or 8 bytes, that's going to change things. In this case, it actually is a byte because it gets treated here as a byte pointer and just loads a single byte from AL, at least in this load. We have field 0x49, which is also an undefined type here. This is also getting treated as a byte pointer. All right. But we can see when this constructor is called, the buffer that's passed to it is allocated as 0x50. So that doesn't match the 0x4a size that we've seen it being used. Now, whether this is just a memory optimization thing or cache thing with alignments, or whether that's the actual size and we just haven't seen it get used yet, we don't know that yet. Let's go to the evtx file destructor because we know that it's used here as well. But it doesn't look like much of it's used here. I need to see everywhere that takes an evtx file. Can I find cross-references to an evtx file type? Let's see. I'm searching for the evtx file type. I found it here in the data type manager. I'm right-clicking it, and I'm going to click Find Uses Of. Now I can see all the functions that Ghidra has identified that uses this evtx file. You can also right-click it and do Find Uses of Field to find uses of a specific variable in that structure. If I do that, I've got different variables that I've defined. It only shows the ones that I've specifically defined and not the ones that were auto-filled by Ghidra. But let's go back to the usage here. Let's see. I'm just looking for maybe some offset access to it where it's close to the end of the buffer. This one's kind of close to the end of the buffer. This one passes through. What's this? This is the EVTX file. This is on EVTX file : clear. And in this case, I could have also found this by just going to the EVTX file class, removing my filters, and looking at all the virtual functions for the EVTX file, which is, our destructor, our clear, get log file info, all of that stuff. Let's go to clear. Clear calls EVT check access, and it passes through as the 1, 2, 3 as the fourth parameter, the 0x48 field. So what is that fourth parameter? That fourth parameter gets checked here if it doesn't equal to 0. Okay, not much really happened there. Let's check get log file info. Get log file info passes it to EVT access check. Does it use it anywhere else? What is this EVT access check? Parameter 4. Surely it's used somewhere. It just checks it here if it doesn't equal to 0. Okay. Let's see if there's any other interesting accesses. Not really. Let's retype this. This is an EVTX file pointer. Let's call this. Again, it gets past the EVT check access. I wonder, is EVT check access documented at all? Now, you may not be able to have the luxury of looking this up in all the code you analyze, but with a lot of Microsoft code, some things can be documented pretty well. Okay, maybe not. You know what? I want to find uses of this field 0x48 because I want to find exactly where that field is used and specifically where is it written to. I'm going to name it unknown1 or unknown48 just to show that it's at access 0x48. Now in my data type manager, I can right click the EVTX file and do find uses of field and find uses of the unknown48 field. Show me where that's being used. Okay. In this location, it's actually being set to something. In this location, it's being set to bvar1. bvar1 is the result of is security channel. That just returns a boolean. Okay, so it's just a boolean. Let's retype it as a boolean. And it comes from is security channel. So I can just literally name it and what does it return? It returns true, I guess, if it is a security channel. So I'm just going to literally give it the name is security channel. And that's a boolean. Okay. What about 0x49? Though that doesn't seem to ever be accessed. Let's see if it is. I'm going to give it a data type of, it's literally a 1 byte field. So I'm just going to give it a car for now, which is a 1 byte field. I'm going to name this unknown 0x49. I want to see if that last byte is, it is used. It's used right here. And that is set to parameter 5. What is parameter 5 to this constructor? Parameter 5 is 1, 2, 3, 4, 5. Here it's 0. Okay. Let me see where it's being used. So again, find uses of field, unknown 0x49. It's passed through as the second last parameter. So parameter 1, 2, 3, 4, parameter 4 to this function. Wait, is that right? 1, 2, 3, 4, 5, 6. Sorry, parameter 6 to this function. How is parameter 6 used? Parameter 6 gets set to parameter 1 plus 0x99 dereferenced. What happens to that? If that equals to 0, then something else. What's parameter 1 here? Parameter 1 here is puvar2. Oh, this is literally just creating. This is a constructor. So this type is going to be an evtx file query result pointer. And, it's a this duplicate name. Why is it a duplicate name? Let's refresh. I can leave it as param1. Let me autofill in that structure. And let's see where parameter 6 is used. Parameter 6 is filled 99 on parameter 1. Okay, where else is filled 99 of parameter 1 used? Well, let's give it a proper type. So the size here is a byte pointer. So let's again name it just a car. And let's name this unknown 99. Now, let's find uses of field unknown 99 for this one. So we're still tracking the use of the field from the evtx file, but now that that's being used in a different structure, tracking the use of that in this new structure allows us to find more usage of that same variable. Here, it's literally just set to parameter 6, and then it's just checked if it's null or not, or it gets set to null. Where's this if line? Yeah, if it equals to 0, then something else gets set. So it is just an if. Okay. All right, so it seems like that is the actual size of the structure. Let me go to evtx file. Let's go to the constructor again, and there's 0x49 used. It really is just used as a byte pointer. So the reason why it's allocated as 0x50 instead of 0x4a when we examine the data type, its size based on the accesses that Ghidra saw is 0x4a. But the memory that gets allocated by the calls to the constructor is 0x50. So why 0x50, right? That is potentially due to alignment. So let's see. If I look at this, we have 8, 4, and then 1, 2, 3, 4 that are unknown, right? So Typically in alignments, you'd have it like multiples of 4 or 8 even. It kind of depends on the architecture and a few other bits and pieces. The alignment can also be specified by you when creating this structure. There's this little alignment field. You can also change it to the machine type alignment, which I think just bases it off the architecture or the compiler specification. You can also mark it as packed, things like that, but that's all dependent on how the structure is actually defined. Is it packed to like 1 byte? Is it aligned to a custom value of like 3 bytes or something crazy? Is it whatever Gidra's default is, or which is just 1 byte in this case? Or is it packed, or is it just a machine? Let's try changing it to the machine alignment, which I think goes based off the compiler specification for the architecture you're working with. If I do that, that changes the alignment to 2. Okay. That didn't change anything, it seems. Everything still stayed the same. Okay. So, but we can see there's gaps that don't get accessed, right? We have 8, 4, and then another 4, which makes it 8, 8. Then you have 8, 8. So you see that the 8s are fine together. And then you got 1, 2, 3, 4, 5, 6, 7, 8. But also these could be accessed in just other functions that don't know that they're actually using the EVTX file type. So it's not properly typed. So Gidra doesn't know that it's accessing these fields yet. But the easiest ones to the easiest ones to spot are the gaps in between. They usually, well, I say usually, but it's going to depend on the target whether they are actual gaps or not. But if the last 2 accesses after this 8 are these 2, which, 40 is an 8-byte boundary, 48 is an 8-byte boundary. What's 48 plus 8 in hex, right? That's 0x50, and that's the buffer that gets allocated. So it's quite likely that it's an alignment thing where the memory is just a multiple of 8, right? Because 0x40 is a multiple of 8, 0x48 is a multiple of 8, 0x49 is not a multiple of 8. So when the machine went to, or the compiler saw that we're using just 0x49 bytes, it kind of just rounded up the allocation to the nearest 8-byte boundary forward, which is 0x48 plus 8, which is 0x50. That's why we saw 0x50 being allocated, but only 0x4a of that size is actually used. So at this point, I can leave it as size 0x4a because that's the actual size of the data, such that any accesses outside of 0x4a is actually going to hit uninitialized data. Now, if it's within 0x4a to 0x50, those accesses aren't going to be outside of the buffer bounds because we saw that the buffer is 0x50. But if that buffer, those bytes that it's accessing in between 4a and 50 have not been initialized, like set to 0 or something like that, then they could contain leftover junk from the heap, which could be an information leakage vulnerability. So we could identify bugs now by seeing accesses that go past offset 4a, but less than offset 50 to this structure. Of course, if it goes past offset 50 as well, then that's straight up a bug as well. But even between, and that you would find as a crash because it would be like an access violation. But you're not going to get an access violation if the buffer is 50 bytes and the size of the structure is 4a, but it goes to access 4b or 4c, because that's still within the buffer bounds. There's not going to be an access violation there. You're not going to get a crash from fuzzing that. But you would have an information leakage bug if that data is not being zeroed out anywhere. And it doesn't look like it actually is being zeroed out anywhere, right? I don't see it being accessed at all past 4a in here. And the code that caused this constructor, when it allocates the buffer, it creates new on it. And what does new do? It allocates data from the heap, and it's just going to return it. That's it. It doesn't zero out the buffer or anything like that. It just allocates it and returns it. There's no zeroing out. At least I don't think heap alloc will zero it out with a zero flag. Let's see. Let's go heap alloc msdn. The second one is flags. If the second value is 0, see, if the second value is 8, then it will zero the memory. But we see here the second value is 0. So it's not going to zero out the memory. So if we could find using a script or something, now that we know enough about the structure, if we saw accesses between 0x4a and 0x50 in that structure in this code somewhere that it's being read from, that would be uninitialized data reads, which could turn into some sort of information leakage, potentially depending on how it's used. But that's cool to know, right? Cool. So that kind of concludes filling out some of the structures and going through that process. It's a very, very helpful process to like turn a disassembly that can look like garbage to something that actually makes sense. But it is just a time-consuming process of doing what we've done through this little walkthrough of finding out how they're accessed, what their types are, give them proper names and things like that.